Changes in matter in a nutshell. So what happens when you change matter? What are the types of changes? There's two general types of changes, physical changes and there's chemical changes. So how do you distinguish between the two? Well, it's based on characteristics. So the most general thing you can look at, any state change going from solid, liquid to gas, any of those three in any sequence is considered a physical change because you're not changing the substance, you're just changing the way it appears. Is it a solid, a liquid, and gas? Prime example is water. Water is ice, water is a gas, water is a liquid. All three of them are H2O. They're water. They don't change their characteristics. It's important to note that. You don't get something new because of it. So physical changes, melting, chopping wood, shredding paper, mixing gray and green marble. These are all things that you don't really change the composition of the substance. You don't make H2O change into a different substance when you go from solid liquid to gas, and even in all these situations. Easy way to look at a physical change, something you could change back. I know what you're looking at, like, okay, shredding paper, how do you get that back? Okay, technically, if you're patient enough, you have enough tape or glue, you can get the original document back. So you're not changing its composition, you're changing the way it looks temporarily, and you could theoretically get it back if you wanted to. Chemical changes, on the other hand, you produce something new. You can get back what you started. When you cook that marshmallow, you can't make it go back to its original form, no matter how hard you try. When a banana rots, you can't unrot it. When you cook something, you cannot uncook it. So the big theme here is that chemical changes you can't undo. Physical, you can. And that includes mixing vinegar and baking soda. You get a gas, a new substance. Fireworks, you can't get the original chemicals used to make the fireworks, no matter how hard you try. Let's try some questions. So magnesium burns when heated in a flame. Is that chemical or is that physical? Well, when you burn magnesium, what are you really doing? You're changing its appearance and what it is. You're making changes to something new. You can't unburn. So the word burn is a quick tip off. It's a chemical change. Magnesium metal tarnishes. So tarnish is a new word, and you're probably not familiar with it. Changes color. It's been oxidized, which basically is a fancy way of saying it reacts with the air and makes something new. Once again, new, so that's going to have to be chemical. You can't undo that. Magnesium metal melts at 922. Keyword there is melts. Can you unmelt something? Yes, you certainly can. That would be a physical change. Grape Kool-Aid lightens when water is added. Why is it lightening? Well, because you're adding water. Doesn't everything get lighter when you add water to it? So are you changing what it's made out of? Or are you making it permanently something you know? Physical change. You can see that's how it plays out. All right, which of the following is not a chemical change? So that means all of these are chemical except this one answer. So match burns. That's definitely chemical. Ice melts. Melts, remember, is a state change. So that's going to be physical. An aluminum door whitens in air. Whitens by itself, that's chemical. You're not adding paint to it. All of these, well, we already know that one of them is different, so that's out. None of these, we know one of them is different, so our answer was B. All right, so here's some examples of other chemical changes, things you can see with your eyes. So it turns out that chemical reactions, you can usually tell in the laboratory based on characteristics. So there's certain things you're going to be looking for. When there's a color change, that is indicative of a chemical reaction or a chemical change. Change in temperature. If you touch something, it gets colder or warmer, chemical change is occurring. Production of a gas. Whether you see bubbles or you smell it, it's going to be production of a gas, and that's going to be a chemical change. Production of a solid. So if you put two liquids together and you get a solid out of it, that's another sign of a chemical change. So these are all different ways you can tell with your eyes there's a chemical change. So production of a gas, whether it's bubbles or smell, formation of a solid. If there's not a whole bunch of solid being produced, you just see cloudiness in the liquid. You won't see a chunk of solid floating in there, but it'll look cloudy, and that's a clue that it's going to be a chemical change, or it is a chemical change. Release or absorption of energy. Change in temperature. So if you notice any change in temperature, that is a chemical change. And color change, you see going from green to blue. And I don't mean by combinations. Like if you mix red and blue together, you get green. Yeah, that's not a chemical change. That's just what you would expect when you mix two different colors together. But if you mix red and blue and you get orange, there's something going on. So that means there's probably chemical change. So these are all ways you can observe chemical change using either your eyes or your nose. All right, physical change on the other hand, you could see at the subatomic level, you're not really producing anything new. CO2, this is dry ice. In case you didn't know, dry ice is just carbon dioxide at a solid state. So when dry ice starts getting exposed to the outer atmosphere to higher temperatures, it changes into its original form, which is called sublimation, changing to CO2. It's still CO2. There's nothing new being produced. So this is a physical change. Here, look, it's solid, right? Now it's a gas, but it's the same molecule both ways. That's what we call the physical change. All right, dissolving of sugar. Anytime you dissolve something, that is always going to be a physical change. That's a really tough one because when something dissolves, people make the assumption is something like it's melting. Melting only occurs when you're increasing temperature. You can't melt a solid when it is being put in a liquid. It doesn't make sense. Like if I put room temperature water and I put some salt in it, that is not melting. Now, if I take, a boiling substance and I put some other substance in it, then there's a potential for melting because you have a high enough temperature to make the solid change to something new. But for our purposes right now, anytime you try to dissolve something in a liquid, that is going to be considered a physical change, not a chemical. And you can see at the submicroscopic level, do you have anything different? No. Look at the sugar molecules, look at the water molecules. They're still there. They just, rearrange a little bit, but they're still intact. You don't see sugar breaking down. You don't see water breaking down. So that's what we call a physical change because you can get back whatever you started. Other examples of chemical change, iron rusting, that's a chemical change. And for those wondering how can you tell? Well, obviously visual, right? See something new being produced on top, changing color. That's a very quick indication that it's a chemical change. At the submicroscopic level, look what happened. You saw how you had this nice geometric pattern. Now look, you see how these little red balls floated in there, the oxygen? Something new is being produced. So that's definitely chemical change. So let's try some questions, make sure you understand it. Determine if the following is an example of physical or chemical. Burning a candle. Well, there's your clue, burning. Anytime you burn something, that's definitely going to be a chemical change. Dissolving sugar in water. Remember what we said about dissolving? You're basically just making it go from solid to liquid. And really what happens, when you add sugar, sugar molecules are attached to each other, and that's why they're visible. You can see them with your eye. When you put them in water, the water attracts the sugar molecules and pulls them away from each other, so now they're invisible. In salt, it takes the Na and the Cl, which are the two substances used to make salt, and it breaks them apart. So when NaCl is together, you can see with your eyes. When they are apart, you can no longer see them. They're invisible. And that's the problem with poisons, right? And you can't see them. Someone sneaks in cyanide into your water, you have no way of knowing. And that's why water quality is a big deal, because you can't see all the chemicals in it, but there are other chemicals besides water. There's different flavors of water, and if you've ever bought water, you know what I'm talking about. Just because water is, considered to have plain taste, there's actually different flavors based on the chemicals present inside of it. All right, so this is definitely chemical change. Dissolving sugar in water. Well, like I said, physical. Boiling an egg. Tough one, because the word boiling is a change of state. That's physical change, right? What are you boiling? An egg. You're basically cooking the egg. That's going to be chemical change. So be careful. When you're boiling food, it's actually a chemical change. It's not a physical change. Boiling water. Water's not food. That's going to be a physical change. Change of state. Cooking pasta. You cannot uncook pasta. Truth of the matter is, some of you guys probably can't even cook pasta. You either make it slimy or you don't know what you're doing. If you're skilled enough to boil an egg and pasta, then I'm impressed. Freezing Kool-Aid. You are freezing it. Change of state. If you've ever tried freezing Kool-Aid because you like Kool-Aid ice cubes dropped into whatever you're drinking, you need your temperature of your freezer below zero, because Kool-Aid actually freezes below zero. A little fun fact. But either way, that's freezing. That's just change of state. That's going to be a physical change. All right, so different ways to separate a mixture. So we're going to first talk about distillation. So distillation is when you have different substances or chemicals inside this solution. So here we have salt water, which is basically NaCl and H2O. So what I'm trying to do is separate these two from each other. So how do I do that? So if I boil it, The NaCl has a very, very high melting and boiling point. It is not going to boil. So if I put this at 100 degrees exactly, the water is going to evaporate or boil. That's what water does, it vaporizes. It's going to go through here as a gas and then through here. What you have here is cooling water running around the tube. So there's a little tube inside of here, and then there's water circulating around that tube. So what is the water going to do? It's going to condense the gas into a liquid, condensation. That's what condensation means, going from a gas to a liquid. So now you're changing this gas to a liquid and you're able to collect it. So distillation is used to separate substances based on different boiling points. So you can also do this with alcohol and water. This is how they make really, really strong alcohol. If you've ever been to a liquor store and see something like, 180 proof of alcohol, this is their heavy duty, crazy alcohol. The way proof works, if you divide it by 2, that's the percentage of alcohol inside of it. So 180 proof beverage is 90% alcohol. That is insane. To put in comparison, beer's anywhere from 15 to 20%. Wine is about 30. This is 90%. You might as well just drink rubbing alcohol. This is when you know you've gone overboard when you're drinking this kind of stuff. That's insane. But you can basically make concentrated alcohol. And the way it works, alcohol is a very low boiling point relative to the water. So water is 100, we know that. Alcohol is around 80, depends on the type of alcohol. So if you make this at 80 degrees exactly, the alcohol will do the same thing the water did with the salt water. The alcohol will change into a gas, get cooled down, and in here you get a higher concentration of alcohol. Why? Because you left the water back over here. When you're producing alcohol, you're going to get water and alcohol together. So this is how you would make a higher concentration of it, in case you're wondering. Next method is filtration. It has to be a solid and a liquid. This is only used when you're trying to separate a solid from a liquid. So if you do not see a solid, this does not work. So you cannot use this for, like, let's say sugar water or salt water. This will not separate those two. Why? Because sugar water and salt water, you can't see a solid, right? It's invisible because it changed into a different form. So no, this will not work. You have to have a visible solid for this to work. And then you're able to collect the solid here in the filter paper. The liquid you can see is clear because there's no longer solid in it. The last method is chromatography. So you can use this to separate dyes that have different colors. So when you have let's say a black dye or black ink, most people think black ink is made just from black. No, not true. So what they do instead, they make it from a combination of different colors. And you're probably wondering, why would they do that? It is cheaper. Everything's about cost. So when you put that black ink here, you put water. So chromatography basically is you have this little container, you have water. And if you put any paper in water, what's going to happen, the water is going to travel up the paper. So as it travels up the paper, it's going to separate into different colors it's made out of. Why? Because the different colors have different attractions to the water versus the paper. So what this means is that the color that likes the water the most is going to travel the furthest. Blue likes the water most. And you're probably wondering, why is that? Because it's traveling with it. There's a thing called light dissolves life we'll get into later. For now, just accept that the further the color is up this chromatography paper, the more it likes the water and less it likes the paper. So which one of these likes the paper the most? Yellow. Why? Because it didn't travel very far compared to red and blue. So black ink is actually made out of yellow, red, and blue, not just black. And remember, that's because it's cheaper that way. You can also do this with leaves if you want to see what different dyes you use inside of it, or different dyes it makes, how it separates out. So this is the different types of change of matter, and this is examples how you could separate matter.